Okay, so this is the written homework for week 12. Fluids, we have, let's see here, 3 problems. Problem 2 is pretty quick, problem 3 a little bit longer, and problem 1 about the same length as problem 3. So let's get started with problem 1. So problem 1 is liquids in a U-shaped tube. So we've had a lot of examples of these in the readings and the PowerPoints as well. So this should look pretty familiar. It says we have a U-shaped tube. It's partially filled with water, and a volume V of a liquid with an unknown density is then poured into the left side. And then the surface of the unknown liquid ends up higher than the surface of the water on the right side. So question A, or part A here, asks us, is the density of the fluid larger, smaller, or equal to that of water? And to explain our reasoning. So the fluid is smaller than water. That would be correct. Does anyone want to explain? Give a little bit more detail as to why? Yeah, go ahead. Mm-hmm. Yep, that's excellent. That's perfect. So this is just basically thinking about, like you said, kind of like an equilibrium standpoint. So you pick 2 heights here, basically, that'll have the same pressure, right? So in a horizontal distance, they have the same pressure. So like this would be P1, P2, for example. So we know that based on that idea, we know that P1 is equal to P2. The same pressure is right there at the same heights, right? And that we know P1 is equal to the density of the fluid, right? Times its gravity, and then the height L, right? And P2 would be equal to the density of water times gravity, and then also times the height on the right. So HL is height on left, HR is height on the right. And so since we know that HL is greater than HR, basically, right? If we also know that this is equal to each other, so if we just kind of substitute these values right here into this equation, kind of like Husmeek said, we'd have P fluid GHL. Let me actually make that clear so it doesn't look like a subscript. GHL, right, is equal to P water times gravity times HR, right? So like you said, gravity will cancel out. They're the same. They're constant, right? So in that case, P fluid times its height should be equal to P water times its height. But we can clearly see here that this height on the left is greater than this height on the right. So if HL is greater than HR, right, this here is greater than this one, then that would mean the fluid, right, the fluid density would have to be smaller than the water density in order for these two to be equal. Does that make sense? So it's kind of like, I guess if you want to think about it, let's say, so if this was, for example, 3 times 4, right? 3 times 4 is 12. We want this also to be equal to 12, right? So I know that the height here is, let's say, 4 centimeters or whatever, right? I know this is 4 centimeters, and this has to be greater than HR. So let's say that this is times 2. So the HR is 2, right? Let's say that's 2 centimeters. So how can I, what number essentially would I have to multiply by to still get 12 on the right side? Just 6, right? So you can really easily see there that the density of water is going to be greater than the density of fluid. So it's kind of like as Meek said, we're just kind of compensating and making sure that you're still in equilibrium. So you have these overall terms all equal to each other. So if I have this height greater than this height, this fluid density would have to go down, basically, or it'd have to be less than. I wouldn't say have to go down, but it has to be less than the density of the water in order to maintain that same, pressure value. So does that make sense for part A? Basically, it's just, first of all, recognizing that you can pick 2 points at the same heights, right, that will have the same pressure. So horizontal distances, right, points that intersect at a horizontal distance, like horizontal kind of like vector there, will have the same pressure. And then kind of anticipating a question someone might have is maybe like, okay, well, why can't I do these two, for example, right? Like these two pressures right here, because they're technically the same height, right? But here you have, basically you're kind of going into the fluid, right? And that pressure would kind of be a little bit different, just because like here we want to basically, when we have two different fluids, right, we want to choose a specific area where you're kind of like at the interface between the two liquids. So if like this one, where you have the oil and the fluid, right, and the water, for example, we want to pick an area where it's just kind of at the intersect between the water and the other fluid, and then use that as our equilibrium height, basically. But yeah. Any questions at all? Okay, cool. So the next part right here, part B, is asking us to determine the density of this unknown liquid if HR is equal to 11 centimeters and HL is equal to 16 centimeters, right? So this is just gonna build on what we did for part A, right? So if we want to figure out the density of this fluid, right? Well, we know G, we know H, HL and HR, right? And we know the density of water. That's a constant. We know that's 1,000 kilograms per meter cubed. So we can just solve for P fluid, right? So we can do like P fluid times gravity times HL is equal to P water times gravity times HR, right? So just a matter of substituting values at this point. So PF times 10, and that's 10 meters per second squared. I'm just going to skip the units for now. And this would be 0.16, right? 16 centimeters is 0.16 meters. We want everything in SI units. And then you have 1,000, that's kilograms per meter cubed. 10 meters per second squared for the gravity again. And then HR is 0.11 meters, right? Or 11 centimeters. And if you go ahead and solve for that, right? What should you get for your fluid density? 687.5. Anybody else get that? Yep, and that's kilograms per meter cubed there. Okay. Anybody not get that or have any other questions about part B? Yep, 687.5, so it looks like everyone is getting that. Anybody have any questions or other concerns about part B at all, or should we move on to part C? Nope. Okay. So I'm going to just move on to part C. So part C is asking us if the liquid was replaced by the same volume of a liquid with even less density, what would happen to HL and HR? and explain. So if we just took this fluid, placed it with another fluid, right, with even less density, what would happen to your HL and your HR? HR would increase. Anybody have any ideas or would like to explain? And this is pretty much going to be similar to what we were doing here, except that now we're kind of manipulating the heights. Okay. So we have two increases and one person who's not sure, so I can probably go ahead and kind of walk us through it. So we're basically kind of going to think about this in the same manner as part A. So we have our 2 points, P1 is equal to P2, right? Those were the points like here and here, right? So we know those are going to be equal to P fluid times gravity times HL and P water gravity times HR, right? So if we were to replace this fluid density with a smaller density, right? The question is now asking us what would happen to either HL or HR. So basically, we can see that a decrease in this density, right, would mean a decrease in the height of the liquid to ensure that pressure remains equal on the two sides. So if this value right here were to decrease, right, then we would decrease the height of this as well to make sure that the pressure remains equal, right? So let me kind of think about it with numbers again. Actually, I take it back, my bad. So let me actually kind of think about this for a second, because I know, so I want to say for sure that HR would decrease. And HL kind of stays the same. So I'm trying to think about this again. What's that? Yeah, go ahead. Yeah, I'm getting a little confused myself, so let me kind of look at this real quick again. So yeah, so I'm thinking though, first of all, just because that you're adding the same volume of fluid, right? Same volume of that liquid on the left, then the height would basically kind of remain the same. But so if this, okay, so if this goes down, right? This stays the same. Then you'd essentially be reaching like a different pressure on this end, and so this height would have to decrease, basically. So I'm not messing at all with the density here. So if I just put like 1000 times 10, right, and then times HR, and I take, you know, this and I make it 500 times 10, right, times HL. So if we were to kind of plug in numbers real quick, right, and solve for HL, let's actually plug in a sample value for HR as well. So let's say that's, I don't know, 0.16 meters again, right? So we were kind of to plug that in, right, and then solve for that. Then we should get an HL of like 0.32, right? Now if we were to decrease this density here even more, right? So we made this like 400 instead, times 10. Well, you're still going to be adding like the same volume, so your height would stay the same on the left side. So we'd make this 0.32, right? But then it's like this part will change, because think about it as you added the water first, right? You added this water and it reaches some height, right? So I add a certain volume of this liquid, right? That's going to still have the same height because I added the same volume. But then this height will change because it's basically, it's like saying it's pushed up more, right? Or pushed up less or whatever. So that height on the right is going to be changing somehow to adjust to this liquid on the left. So this liquid that I'm adding, it has a constant volume, and it'll have a constant height that's added, right? But then this height on the right here is going to respond to the addition of that liquid. That's the way to think about it, essentially. So this height on the left will not change, but the height on the right will change in response to that. So for the height on the left, it's just thinking about, I'm trying to think about it, I guess, to think of a different kind of analogy to relate it, but it's really just about the kind of like the amount or the volume of liquid added. So I guess, okay, so I'm not really sure how I can draw this without like having some kind of animation or whatever, but let's just say, kind of think about it this way. So I add this certain amount, right? This is my first amount that I'm adding, so it has a density. So I'll say P fluid 1 is greater than P fluid 2, right? So this is the first amount I added, and then this is the second amount I added, right? So this was like the 500, and this was the 400, right? Kilograms per meter cubed. So if I add this certain amount right here to this definite amount of water, right, it's going to push it up a specific height. So let's imagine too that this tube was like this before, right? So the water was up to here, basically. And then I added all of a sudden some fluid to it, right? And so it kind of pushes up the water level to like this height, for example. So this is the height on the right. So now if I change up this liquid that's added here, right? I add one that's, less dense now. I'm still adding the same amount, right? So like there's a specific volume that I'm adding, right? And so if I were to just basically, start over essentially, and I have the water at the same height here and here, right? So I'll just draw this in as water. And I add a less dense liquid, same amount of liquid that I added, but it's less dense, right? So think about being less dense, applying like less pressure or less force, basically, pushing it up here. So maybe instead of going up to a height of, 0.16, I might go up to 0.08, for example, right? So that would be kind of that'd be the way I would think about it in real life. Like if I just added, or not even added, like if I just thought about pushing down on the liquid, right? So if I have something more dense, I'm pushing more on the liquid, so that liquid goes up on the right to a higher height, basically. But if I, add a liquid the same amount, so the same height of liquid on the left, but it's less dense, it's like I'm pushing with less force, basically, and causing this height here to go up to a lesser value. So if I put a lot of pressure here, right, if I add something that's really dense, it's going to push it up farther, basically. But if I add something that's like less dense, right, it'll still push it up, but by a less amount. So the height on the right would decrease. Does that make sense? I really hope that makes sense. Like I saw a person leave, and I was really doubting my explanation there. Yeah, go ahead. Okay. Mhm. Yeah, go ahead. Mhm. Mhm. Yep. Basically, yeah. Mhm. Okay, I'm just making sure because that Loki I saw a person leave, and I was like, darn. Yeah. All right. I'm hoping that made sense for everybody as well. If anyone needs me to reiterate it again, I can do it again as well. So, um, but I think the person who initially asked the question was Caroline about the how the height on the left would stay the same because the new liquid is less dense. But does that make sense? Because it's like you're adding this specific amount of liquid, right? So I'm adding, just let's say 15 meters. This is horrible an example, but like I'm adding 15 meters cubed of, this liquid. So it's going to take up the same amount of space, take up the same height on the left, right? Because, like I said at the beginning, you start off with like the water in this U shaped right here, in this U shape right here, right? So if I'm adding this liquid, it's going to be a specific amount that's going to be taking up a specific height, right? At the same time, that specific amount of liquid is going to be exerting kind of a force here that's going to be pushing the water on the right from this level, right, to this new level here, this height R, right? So if I added a more dense liquid, it's going to be pushing with more force, basically, right? So I'm going to reach this height, for example. As soon as I remove this liquid and add it with the same amount, just less dense, it's going to be exerting basically a lower or a smaller amount of force. So it might only push it up to like this height. And we can kind of check that with the numbers where, like I said, if you had, 500 and 400, right? Those are your two densities for that liquid. I'm still adding 0.32. Well, like my height is 0.32 because it's the same amount of liquid that's being added, right, on the left. But then if I go ahead and calculate then 1000 times 10 times HR, right? If I were to calculate HR, and keep in mind this is 0.32 as well, then HR would give me what? So times 10 times 0.32, 1000 times 10. So then I'd get like 0.128 meters for HR. So you thought about it? Oh yeah, that's a hypothetical example, yeah. No, no, no. Mm-hmm. This is just an example to kind of show like the mathematical relationship. So Caroline, you thought about it as if Yeah, go ahead. Go ahead. Were you asking something? So they don't. I don't. I just provide kind of like the equation, plugging in the numbers just to kind of help you guys visualize it. But they won't take that pretty much as a I guess an explanation, because they're more looking for like how you can relate the variables and stuff to each other. So finally, like as a final explanation, I would essentially say that since the volume of the fluid that's added is the exact same, right? I'm adding the same amount of fluid, because they said in the problem, if the liquid was replaced by the same volume of a liquid, right? So the same volume, and the area of that tube, that cross sectional area hasn't changed at all, right? So I'm adding the same volume, so HL would stay the same as before, but then since the density is smaller, right? For that left, like that liquid on the left, then HR will be smaller than before, because it's kind of like that other problem as well that we did before, right? So that 3 times 4 equals 6 times 2. So if I had then 4 here again, right? So I'm keeping the same height because I'm adding the same amount of liquid, right? I'm adding the same amount of volume, right? So this height would stay the same. And I, added a fluid with a density of 2 now, right? So this is 2 times 4 is equal to 8, right? Well, the density of water is going to stay the same. Density of water is just water, so that's 1,000 kilograms per meter cubed, so that's 6, right? So then all of a sudden, I'm looking for what's HR, so that HR is going to be like 8 over 6, right? Which is, whatever that is, right? That's just going to be smaller. So just that kind of mathematical relationship, I would write those equations out just to kind of show what the variables are. I wouldn't add any numbers or anything, but just basically explain that since the amount of volume of the liquid is the same, it'll reach the same height on the left, but that would change the pressure value, right, at those equilibrium points. So in order to compensate for that, we would have to have the HR be smaller to maintain the same pressure, basically. Mm-hmm. And Caroline, going back to what you said, so if the right is decreasing, the water is pushing the left side liquid higher since it's all connected basically in the same tube. But that, I mean, you could sort of kind of think about it that way, but the thing is that we already have the water um like there. And so if we add the liquid, it's going to be pushing it, right, at some amount. It's just yes, it is less dense, right? So um thinking about the water pushing the liquid sort of makes sense, but the thing is that since we're adding that liquid with the same amount, right? So we're adding the same amount of liquid, it's going to be taking up the same amount of space, so it's going to be the same height, right? So it's like, once again, thinking about this as a cylinder. So if I'm adding 15 meters cubed, right, and I have this much space to work with, so this much space right here to work with this area right here. So if I'm adding 15 meters cubed, it's going to take up 15 meters cubed, right? And so that's going to be reaching the same height, because this area, this cross-sectional area, like the radius and the diameter, all that stays the same in that tube, right? And if I'm adding the same amount of liquid, if I'm adding the same volume, well, the height has to be the same. So once again, if I kind of just do numbers, I'm sorry if I'm taking too long on this problem, just want to make sure that everyone is in the loop with this problem. So if I said, this area right here, right, or let's say the volume of the cylinder right here, that's pi r squared h, right? So here's your height on the left, and then this is your cross-sectional area. So this is just like the circular part of the tube, basically, just the area right here, the circle. That's going to stay the same because the tube hasn't stayed the same, or the tube stays the same. Jeez. So this is constant, right? Well, if I add the same amount of volume, if this is 15 and this is 15, right, and the area is the same, the cross-sectional areas are the same, well then, if both are 15, for example, then the height of that liquid has to be the same in order to take up the same amount of volume. That's the whole idea. It's one of those problems where like your intuition kind of confuses you, because trust me, like I thought about this problem 100% at the beginning, that if you were to add a less dense liquid, it would basically push the water up like this, this way, or push the liquid up. So, yeah. But since they have the same amount of volume added, the height on the left would stay the same, but that height on the left is the same with a smaller density. So with a smaller density, the height on the right would have to increase in order to maintain the same pressure. Okay. I'm really hoping that makes sense. Like I swear, like I don't honestly have a better explanation of like why it wouldn't be the other way, Caroline, just because like that totally, like in my mind, outside of a physics perspective, like that would kind of make sense, right? That would be the way to kind of think about it. Just using intuition, I suppose, but this is just one of those problems where like you have to kind of ignore what you think might happen in the real world and then just kind of like think about it just solely from a physics perspective. Look at the relationships between the variables and whatnot. But hopefully that kind of clears things up, because it's the whole like volume aspect. Since the volume is the same, the height would have to be the same on the left. So, you know, keeping the height the same. No, go ahead. Less of the liquid. Yeah, that makes sense as well. But yeah, it's just with this fluid chapter especially, like I threw out my intuition out the door. So I like you really have to kind of just look at the variables and stuff, as opposed to just kind of thinking about like what could happen if I did this in real life. So hopefully that kind of clears things up. But yeah, finally, height on the right would decrease. HL stays the same. And I can, you know what, just because I feel bad for sounding like an absolute fool, I will kind of write this out here as a brief kind of explanation. So, basically, since okay, I really like to make it in red. Okay, since the volume of the fluid is kept the same and nothing about the tube has changed, the height on the left remain the same. However, with the height remaining the same on the left with a smaller density value, the height on the right would have to increase in order to maintain the same pressure, according to P fluid times G times HL is equal to P of water times G times HR. That would be kind of finally how I would go about saying that. Alrighty. If everyone's all good for part C, we can probably move on to part D. Okay, awesome. Alrighty, so for part D here, it's saying the density of the unknown liquid is decreased to half of what it originally was. Find HL and HR. So, kind of like what I did earlier, just with numbers now. So, what did we have here before? So density is decreased to half, and then in that case the HL on the like the height on the left would remain the same, but it's not 0.32. Sorry, it's 0.16. So we had our fluid density was 687.5, right? So half of that basically is going to be what, 343. So P fluid once again times G times HL is equal to P water G times HR, right? So this is like 343.75 kilograms per meter cubed times 10, and then times 0.16, which is the same height, and then times 1,000 kilograms per meter cubed for the density of water, multiplied by the acceleration of gravity, which is 10 meters per second squared. And then we can figure out the HR here, right? So we know that HL is equal to 0.16 because we're adding the same volume here, basically. The density will decrease to half of what originally was, but the volume is the same, and so the height reached on the left is the same. But yeah, that should give us HR, right? So we should have 0.055 meters, yep. And that's 5.5 centimeters as well. Does that make sense for part D? Basically what we did conceptually for part C, but then we actually plugged in numbers this time. No, the height on the left would stay the same. Yeah, sorry. Because it was half the density, right? But the same amount of volume, basically. So it's exactly kind of like what we said for part C. Decrease. Yep, because we see here that our height on the right was actually 11 centimeters, and now it dropped down to like 5.5. Yep, decreased by half as well, because like if you think about it, if you decreased, like I said, like if this stays the same, this is constant, this is constant, this is constant, right? I multiplied this by 1/2, then I would multiply this by 1/2. So if you just take 1/2 times the height from before, which is 11 centimeters, 5.5 centimeters is exactly half of that. So, yeah. Yeah, it's a direct relationship. So if you just multiply by 1/2 on one side, so multiplying the density by 1/2, you should multiply the height on the right by 1/2 as well. But yeah, hopefully that makes sense for part D. Any questions at all? Okay. We'll probably move on to part E then. So now it says, suppose the unknown liquid had a higher density than water. So if the fluid density was higher than water, if the unknown liquid stays on top of the water, how would HL and HR compare now? So if, oops, P fluid is higher than P water now, how would HL and HR compare now? So, oops, I don't know why that deleted. It's kind of the opposite of what we did before, so, or similar at least to what we did before. So if we had, once again, P fluid, right, times G times HL, P water times G times HR, right? So HR would increase, right? So HR would be greater than HL, right? So HL will stay the same regardless because you're adding the same amount of fluid, right? The volume is the same. But then all of a sudden, this is greater, right? So the density is greater now. There's a higher density. So if this is higher and this is kept the same, right? Then, because of that direct relationship that we were talking about before, HR would have to increase. But yeah. And so, what you can say is, very generally, you could say that HR would have to increase. Would increase, right? Due to the increase in the density of the fluid. So it's sort of like that pushing down, like I said before. So if I add a denser fluid, right, it's going to want to basically push down more, so it's going to increase it to a bigger HR, right? HL will remain the same, right? It's the same amount of volume being taken up, but I'm essentially pushing down harder, right? This is just very informal, but I'm pushing down more essentially to get to a larger HR. And would an HL decrease if it's pushing more? No. So, once again, like I know it's like it's the issue with the whole intuition thing, but just looking at how much like liquid we're adding, right? I'm adding the same volume, right? So if I go back to that, volume is equal to pi r squared h, right? Pi r squared is the cross-sectional area of the tube. That doesn't change. Like the width or whatever of the tube, that doesn't change. And if I kept the volume the same, right? So I'm adding the same volume, I would have to reach the same height. So it's like if I added 15 cubic meters right before and added another 15 cubic meters, it's just denser. Because I'm adding the same amount, I'm adding the same like volume, right? The height on the left would continue to remain the same. It's just that now that height on the right is going to be changing up just because it kind of feels like a force exerted on it by the other liquid. Yeah. Yeah. So since your fluid on the left is going to be denser, but you're adding the same amount, right? So it's just like amount versus like density, right? So if I'm adding the same amount, I'm adding the same volume, right? Then my height would remain the same. Oops. but yeah, your density, like a greater density on would kind of push that the water on the right to go up higher, basically. Yeah. I'm just going over it one more time just to make sure that it all kind of makes sense in my head as well. Yeah. And in fact, we can also kind of say that HR is actually greater than HL, right? Because if we think about it, if we take the density of the fluid, right, and we know that it's greater than the density of the water, so P fluid over P water, right? If we take that ratio, since the fluid density is higher than the density of water, well, that's just going to be that ratio right there is greater than 1. So if that ratio is greater than 1, well, we know that the ratio of H, I guess, I don't know how I'd say it, kind of relate this to height, but I don't know if it should be HL over HR or HR over HL. Forget it. You don't have to like say which one is greater than the other. It's just saying what would increase or what would decrease, or stay the same or whatever. Well, that's what you meant, HR over HL? I mean, yeah, I mean, you don't really have to kind of say specifically which one is greater than the other. I just went ahead and said, like, what would happen to each value. But yeah. Does that make sense to everyone? Any questions about anything in problem 1? All good. Okay. All right. We can probably move on to problem 2. So problem 2, we have blood flow. So this is a nice change of pace, I guess, from this past problem. So we have the carotid arteries carry blood up through the neck to the brain. In one patient, they are 11.2 centimeters long and have an inside diameter of 5.2 millimeters. Assume the speed of the blood at the bottom of the artery is 0.5 meters per second, and the density of the blood is 1,050 kilograms per meter cubed, right? So now part A is asking us by what amount does the pressure drop in one of these arteries from bottom to top? So what's the pressure drop? So when we say pressure drop, right, then that's going to be indicating some kind of change in pressure, right? So like delta P, right, our change in pressure. And we can say that that's PF minus PI, right? And that's just You could say like that's PB minus PA or PA minus PB. Whatever it is, you're just going to either get a negative or a positive answer. But I'll just say PB minus PA so we can get a positive answer, so we can say that it drops by this amount, right? Anyway, so that's going to be kind of how to set it up first, to recognize that pressure drop means a pressure change, right? So we were going from bottom to top. So if we were to think about this and kind of draw it out, right? If you had an artery, bottom, top, and I'll just call this A, right? As in top, and this is bottom, right? So, we want to figure out how much this pressure changes from here to here. So we have value of the density, right? And then what else do we have? We have the length, basically, of the artery, right? So this could be this part right here, this whole length right here, and we can kind of think about that as the height, right? So now that we have those values, we have pressure, we have, or my bad, we don't have pressure, sorry, I meant we have the height and we have the density of the blood. How do you think we can go about figuring out the change in pressure? So like I have a PB and a PA, right? Those are two separate ones. And I'm trying to figure out like the change in the pressure, right? So is there any way that I can set up an equation of some sort that I can have PB minus PA on one side, for example? Or an equation that would help me figure out, you know, or have PA or PB on separate sides of the equations? Any ideas? So yeah, we have PB minus PA is change in P, but then how can we relate that to density and length and all that, right? How can we figure out, because we don't know PB and we don't know PA, right? Those are unknown values. So there we go, excellent. So PA plus PGHA is equal to PB plus PGHB, right? Hydrostatic pressure equation, yep, excellent. So that kind of allows us to think about this as in a way of saying as like PB, subtract over PA, PB minus PA, and then subtract over this value, right? I solve for that. I can write delta P on one side, and then I can say PGHA minus PGHB, and then solve for the delta P that way, right? So I can set this up. I don't know PA. I know the density of the blood is going to be 1,050 kilograms per meter cubed, right? Times 10 meters per second squared times the height at A, right? So this kind of just depends on how you want to set up your height values. I just usually put like my B, like as in my bottom, that's at 0 meters. And then whatever it is, like my A, my other value that I'm looking for, is that's my height, basically. So the height at A is going to be 0.112 meters, right? Because that's just the 11.2 centimeters. That's the height there. It's the length of the artery. So that's 0.112 meters, right? And then I have PB. That's unknown as well. I have the density again of blood, which is 1,050 times 10 meters per second squared. And then HB, which is 0, right? Because I'm starting here at 0 and going up to 0.112, right? So effectively, this will cancel out because it's just going to end up being 0. And then I can solve for PB minus PA, right? PB minus PA. Can subtract over the PA. And then figure out what this is, right? So PB minus PA, right? And that's equal to delta P is also equal to 1,050 kilograms per meter cubed times 10 meters per second squared times 0.112 meters. That'll give me the pressure drop, right? And that should be, yep, 1,176 pascals, right? So you can say then there's a pressure drop of 1,176 pascals, right? Alternatively, you could have set this up as PA minus PB. You'll get the same value. It's just now you have like negative 1,176, which makes a little bit more sense because then it kind of indicates with the negative sign that there was a decrease in pressure, right? The delta P was negative. So going from bottom to top, the pressure dropped, right? Your final pressure was smaller than your initial pressure. But I just like, I don't know. I just like having positive answers, and then I can like indicate the direction or what's going on, right? Separately. So I can say 1,176 pascals dropped, right? Or I can say there was a pressure drop of 1,176 pascals. But if you prefer saying PA minus PB and then you get a negative answer, and that indicates already with the negative answer that pressure has dropped because the delta P is negative, right? Then you can say that as well. But yeah. Makes sense for part A? Yeah. So yeah, you can say it dropped by that amount, or you can just, if like I said, if you switch around the variables PA minus PB instead, you'll get a negative answer. So you get like negative 1,176 pascals, which that negative sign in and of itself will indicate that pressure has dropped. But yeah, fair enough. Makes sense for part A. Any questions at all? Okay. All right, cool. Part B now. So it says one of the arteries has a stenosis at the top where the diameter drops to 3.4 millimeters. By what amount does the pressure drop now? So before we go into any math or think about any equations or anything like that, let's just kind of think about this conceptually. So we have an artery, right? This is a healthy, normal artery. And there's blood flowing through it normally, right? And then all of a sudden, you might have like kind of a blockage or a narrowing of the artery somehow, right? Where there's essentially like less space for the blood to kind of flow through, right? So we have that diameter there is decreased, right? And that there's a narrowing of the artery. So when you have blood flow, right, there's a specific kind of equation for that, right? So there's amount of volume per unit time, and then there's a flow where we say the area times the speed, right, or the velocity or whatever. Right? So if we think about it, there's a decrease in area. That artery is kind of narrowing, right? So the diameter is getting smaller. Now, we know before, though, that, well, okay, area is getting smaller, so what? Does the flow change if area gets smaller? Would it? If just the flow, like just like the, let's say, kind of like the amount of, blood cells moving through that artery at a unit, specific unit time or something. Does that flow change? Or would the flow remain the same, or what would happen to it? So the area gets smaller, right? But the flow would have to be constant. The flow would have to remain the same. So there has to be like your flow is conserved basically. So it's kind of like law of conservation of energy or whatever, right? So you have a constant flow. That flow has to remain the same, but there is some kind of change, right? So in response to that change, right, what does our body do if there's like a clog, right, in an artery or something like that? Well, it starts to work harder, right? And that working harder can kind of translate to, as people have said in the chat so far, that the velocity will change, right? So if I want to maintain, right, a specific Q, if I want to maintain this value, right, and all of a sudden my area changed, like if artery gets clogged up, right, so there's a smaller area to move through, well, I want to basically get the same amount of blood to all of my cells, right? All of my cells need this specific amount of blood, so I have to keep the flow the same, for example. But if the area decreased, well, I have to kind of work harder to push that same amount of blood. So if this has to stay the same while this decreases, then my velocity or my speed has to increase. So you have to pump blood really, really fast to get the same amount everywhere when an artery is clogged up or whatever, right? So given that the area has decreased and we want to keep the flow the same, your speed of that blood flow will basically increase to maintain the amount of flow, right? Now, since we kind of understand that now, right? So we know that our velocity is going to change, or our speed is going to change one way or another, right? So if we're going 1 meters per second, we'd have to go 2 now or something, right? Now, how can we kind of relate that to a pressure drop, right? So how can we figure out basically what goes on in that artery when we're having that decreased area increase velocity, right? So this was also kind of a conceptual thing that I hope you guys kind of went over. But yes, there is a formula that's really similar to this one, but it now includes the velocity and all that. But basically the idea is that if you're in a higher pressure area, right? I think it's that your velocity or your speed will go down, but in a lower pressure area, your speed will be greater. And so that kind of makes sense because it's like here in this area right here, I have a lower pressure basically, right? But here I have a higher pressure. And so, or do I have that mixed up? I can't remember. I don't know if I have the pressures mixed up, but basically it's like you kind of have to speed up when there's a change in pressure here. So when pressure increases, you kind of have to speed up your velocity, while as when you have lower pressure, you don't. So with that equation, it's going to be pretty similar. It's just that now you're adding this part right here. So half times the density times your velocity at point A squared, and then PB plus PGHB again, plus half times density times the velocity at point B squared, right? So we know that speed at the bottom, right, was 0.5. So This is V bottom, right? This was 0.5. Now we got to figure out what it is at point A, right? And we can kind of figure that out using this equation. A1, or let's say AAVA is equal to AB VB, right? Which is just an extension of the whole, like, flow has to be the same. So Q equals Q, QA is equal to QB, right? But now there's a change in the area, right? So we know the area is pi r squared, right? So pi times, what was the radius from before that they had? So at the top, the diameter drops to 3.4 millimeters, right? So 3.4 millimeters, divide that by 2, and then convert to meters. That should give me around, what, 0.0017 meters? So that's my radius. And this is at the top. A is at the top, by the way. A top, and the diameter at the top was 3.4 millimeters, right? So that's 1.7 millimeters, and then convert that to meters should give you 0.0017, right? And then multiplied by the velocity at A, which I don't know yet. But then, oops, I can look at the area for B, right? And that was pi times 0.0026 meters squared, right? Oops. And then I can multiply that by the velocity, right, from before, which is a 0.5 meters per second, right? And then I can solve for VA. So I want to figure out what the speed is at the top, because I know what the speed is at the bottom, right? And since there's kind of this speed change, right, the pressure would have to change. So VA would be 1.17, yep, meters per second. And then I can go back and pretty much plug in VA here, plug in VB there, and then plug in all the values that I had from before, right? So I know I'm looking for the pressure drop again, which is like the PB minus PA that we had before, right? So I can kind of subtract this over and make that delta P, right? This is delta P. And then I know from before that the height at the bottom, I set that at 0, right? Remember when we canceled that out here? So 0 meters is at the bottom, and then the top would be 0.112, right? So this effectively canceled out because HB is equal to 0, right? And then this is going to be what? So we have 1,050 kilograms per meter cubed, right? That's our density for the blood, times 10 meters per second squared, times our height, which is 0.112 meters, right? That was the length of the artery there. And then we're going to add that to 1/2 times the density times 1.17 meters per second, and then square that, right? That was our VA. And then over here we have, remember we subtracted PA, so we have PB minus PA, which is delta P. And now we also have plus 1/2 times the density again, right? And then multiplied by our VB, which was 0.5 meters per second, and then square that, right? So we had the bottom of the artery had a speed of 0.5 meters per second, right? So we can then kind of subtract values over. We can subtract this whole term over, add these up, right? And then that'll give us our delta P. Yep, sounds about right to me. 1762.87. I think I had like 1763.4. That's pascals. That's a pressure drop there. So it drops by 1762 or 1763 pascals. So kind of wrapping that up from a more conceptual standpoint and kind of amending my statement earlier because I think I had messed it up the way I said it. So since there's a pressure drop, right, from bottom to top, that pressure is dropping due to that narrowing, right? So when there's a pressure drop, the velocity or the speed, right, of that flow of blood will increase. And then when the pressure is greater in like these areas, right, then the velocity is lower, right? And I can show exactly where this kind of comes up in the lecture, I believe. I can show it here real quick. Oops, that's the reading. Yeah. So pressure is higher when the fluid is moving slower. So like in this area here, like remember like where we said the artery, right? So the areas that weren't clogged, the areas that were normal, right, and healthy, the fluid is moving slower. So it's smaller velocity here and higher pressure, right? And then lower pressure here where the fluid is moving faster. So higher pressure, slower moving, so high P, slower V, and then low P, faster V. Let me write that out again. So low P, high V, and then high P, low V. So it's kind of like an inverse kind of deal. So there's a slower moving fluid and under high pressure conditions, and a faster moving fluid in a lower pressure condition. And this is a really important concept to know here. I would very much go over that. But yeah. And the way they kind of go, this kind of might seem counterintuitive, but the way they kind of think about this, right, is it's like here's where everything kind of starts to narrow, right? So I'm going to be moving at a faster speed right here regardless. Like I know for sure, like if I have like a hose or something, right? And I like, let's say I kind of tighten it up a little bit, right? If I grasp on it really tightly, right? There's going to be water flowing out really, really fast, right? So you might think that this part right here has higher pressure. But the thing is, it's a little weird how they kind of define it because what they're saying is to reach a higher speed here in these areas where I have a wider kind of, room basically, right? I'm going to have to increase pressure here, right? And pressure I know is force over area, right? So if I want to increase my velocity, right? Well, increasing velocity means that I have to apply some kind of acceleration, right? So I know that force is equal to mass times acceleration, right? So if I want to accelerate this fluid, if I want to make it move faster in these tighter areas, basically, then I'd have to apply some acceleration, right, to make the velocity increase. And so if I'm applying some acceleration, I'm increasing the force. Force goes up, right? And so if force goes up, right, force over area, then pressure goes up, right? So it's like I have to increase pressure while I can in this healthier area, right, to make sure that in this tighter area that's unhealthy, like just talking about arteries here, right, then if I increase pressure here, while I can apply some kind of acceleration to make sure that blood flows faster here. Does that kind of make sense? I know it's a little bit confusing just because, like, clearly I would think that, you know, this is wider, so it's like you have low pressure, and this is tighter, so you have high pressure, right? And that's how we kind of think about pressure. But in this case, it's like I need to apply a higher pressure in this area to make sure that the fluid, once it reaches this part, it flows really fast. Does that make sense? So it's like applying pressure, not necessarily like what the pressure, I guess, might kind of be specifically at that point or whatever when you're having flow. So I have to apply a higher pressure here to make sure that my force, right, over area, so if I apply greater force, right, if I have a higher pressure, I'm applying some acceleration so that make sure that once I get to this narrow area here, the velocity will increase. But yeah. And then your pressure drop should be a drop of 1763 or 1762 pascals. But yeah. Any questions about problem 2? Nope. All right. Problem 3 is all that's left. I think this should go a little bit quicker. I'm hoping, at least. I think maybe the last part is what might give us a little bit of trouble. Parts E and F. But yeah, so problem 3 is an open tube pressure gauge. So it says a pressure gauge can be made with a vertical tube that is open to the atmosphere. The higher the pressure at point A at the bottom of the tube, the higher the water in the tube will be. So the higher pressure at point A at the bottom of the tube, the higher the water in the tube will be. Okay, so part A is telling us, or asking us, what is the speed of the water as it enters from the left? So they've given us that this area here entering to the left, the cross-sectional area is 10 centimeters squared, right? And then we have this cross-sectional area is 5 centimeters squared with a speed of 4 meters per second, right? Well, if we think about it, right, this speed here multiplied by this cross-sectional area, well, is going back to the flow like we said before. So if I want the flow to remain constant throughout this whole thing, right, then what has to happen? So if I have, Q1 is equal to Q2, then I can say like A1 V1 is equal to A2 V2, right? So the flow in has to equal the flow out. Excellent. So the flow in to the tube has to equal the flow out of the tube, right? So if I know the flow in has a cross-sectional area of 10 centimeters squared, right? I want to figure out the speed, and I know the going out it has a cross-sectional area of 5 centimeters squared, and I know that's 4 meters per second, right? I can just solve for V1. And the reason why I didn't convert centimeters to like meters squared or whatever is that these units will cancel out anyway. Everything is the same. So as long as like all your units kind of match on each side, you'll be good. Unnecessary to convert that to meters cubed, or meters squared, sorry. So your V1, yep, should be 2 meters per second. And that kind of makes sense, right? Because just imagine kind of like a hose again, right? So if I, or that blood, or with the artery, right? So if I basically tighten this up, right, where I go from 10 to 5 centimeters squared, right? I decrease the area, I decrease the cross-sectional area, I kind of squeeze it, I narrow the opening, right? Then my speed will increase. But yeah. Makes sense for part A. Any questions at all? Okay. If no one has any questions for part A, we can move on to part B. So part B is asking us, so it says diagonal tube has the same cross-sectional area as the outgoing horizontal tube or horizontal opening. What is the speed of the water at a height of 2 meters? So diagonal tube has the same cross-sectional area as the outgoing horizontal tube or horizontal opening, right? It's just asking us what is the speed of the water at a height of 2 meters. Well, if the area is the same, then what? Remember we were talking about how like the flow inwards has to equal the flow outwards, right? So technically, if they're saying that the diagonal area here has the same cross-sectional area, right, then your speed will change at this point, right? So we know that we started out with 2 meters per second here. As soon as we hit this part, it's going up to that 4 meters per second, right? So what does that mean? At a height of 2 meters, so if we started out with 2, right, and we're ending up with 4 meters per second, and we want to keep the flow the same, well, if we know that, so like if we said this is the opening, right, this is the opening, and then this was the outgoing area, right? Well, we know that the outgoing area has the same cross-sectional area as the diagonal area. So, like Caroline said, it should be 4 meters per second, regardless of what height I'm at, because the cross-sectional area is the same. So, like, if I didn't know what this value was, if I just knew that I came in 10 centimeters squared at a speed of 2 meters per second, right? Then I'm asked, like, okay, well, what's the speed at a height of 2 meters or 2.5 or 2.3 or whatever, right? It doesn't matter what height they're asking me for, nor does it matter if they ask me here, right? Because as long as the cross-sectional area is the same, that speed is going to be the same. So at a height of 2 meters is the same as a height of 4, is the same as a height of 1, whatever, right? Just because the cross-sectional area is the same. So like the diameter, the radius, whatever, the length, the width, whatever, right? That's all the same. So since I have the same cross-sectional area, my speed would continue to be the same, 4 meters per second outgoing. So, I can say like in the opening, A1V1, right? I have 10 centimeters squared times 2 meters per second. And I could say like my outgoing has to equal the same, right? So my outgoing should be the same. Now, given the diagonal area has the same cross-sectional area, right, as the outgoing, right, then A2V2, right, 5 centimeters squared, right, times that velocity, right, or that speed, oops, should still equal that 10 times 2 from earlier, so V2 should still equal 4 meters per second. So I would make sure in your answer to include the constant flow equation right here. A1V1 is equal to A2V2. Since my incoming is 10 times 2, right, so I have a specific flow incoming, that same flow has to be outgoing, right? So I also know now that the diagonal area is 5 centimeters squared, right? It's the same as the outgoing from part A. So regardless of the height, as long as the cross-sectional area is the same, according to the constant flow or the continuity equation, right, my speed would have to be the same. It would have to be that 4 meters per second in order to maintain the same flow. Make sense for part B? Okay. Fair enough. Part C now is asking us what is the absolute pressure at point A at the bottom of the vertical tube. So they define this as point A, right? They want us to figure out the pressure at point A. And then, yeah. So I guess I'm kind of thinking about this real quick. So pressure at point A at the bottom of the vertical tube. Yeah, okay, yeah. So we're looking for PA, right? Do we know any other pressure values? Because PA is unknown, but do we know any other pressure values? So we know pressure at the top here, right? That's 1 atmosphere, right? Because that's just in contact with the atmosphere there. But at the same time, there's another area that we should know. And it's also 1 atmosphere. Exactly, the opening at the right. So right here, because it's also in contact with the atmosphere, that should also be 1 atmosphere, or 10 to the 5 pascals. So we could think about this part right here, right? But we do have a lot of values and a lot of, information that we know about with this area right here. Because I don't think we know the height yet. For this part to have enough information to kind of use this as our point B. But we can use this as our point B because we know that this height is 4 meters, right? From point A right here to that point B is 4 meters. So, and we also know a lot about like the velocity and all those values, right? So what equation do you think we can use to relate pressure at point A to the atmospheric pressure that is at point B, and then also factoring in that the fact that there's a pressure change because this cross-sectional area is changing. So the one with the velocities, yep. So we have pressure A, right, plus PGHA plus half PVA squared, right, should equal PB plus PGHB plus half PVB squared, right? So from the get-go, we can kind of eliminate this, right? oops, because we can set our height at A to be 0, right? And height at B to be 4 meters. So we can kind of arbitrarily set that. And so if our height at A is 0, then this whole value becomes 0 here, right? And then we know our speed at A from before, right? That was what, 2 meters per second, right? That was the coming in. So we can plug that in here as well. And we know our density, and we're looking for our pressure later, right? And then at the same time, we know that pressure B is going to be the atmospheric pressure, right? The 10 to the 5th pascals. And then this is 1,000 again. This is the density of water, 10 meters per second squared. And then our height B is 4 meters, right? That's the height from here to here, right? This part right here. And then we know our density again. And then our value for the velocity here, or the speed, is 4 meters per second. And that's this one here as well. Yeah, so 4 meters per second. So knowing that, we can just kind of plug things in, right? So we have PA plus half times 1,000 kilograms per meter cubed times 2 meters per second, and then square that, times, or is equal to 10 to the 5th pascals, right? That's our atmospheric pressure, which is this area here that comes into contact with the atmosphere. That's our outgoing area, right? And then we have 1,000 kilograms per meter cubed, right, times 10 meters per second squared. And then times our height, which is 4 meters. And then half. Let me actually go ahead and erase the units here. The reason why I don't write units a lot for this chapter is that the equations are so long that it's just not as time efficient, especially like for the homework. While I'm explaining it, that is, to write everything out. But for sure, when you're actually like doing this on your own, and writing things out, 100% put in the units, because otherwise they'll count off. I'm just not putting in units now, just so it's easier and I can get through it quicker, and I don't have to like mess around with the size of my handwriting and stuff. So we have 1,000 kilograms per meter cubed, and then times our velocity, which is there's like an instinct to write the units, I'm sorry. And there's 4 squared, right? 4 meters per second squared. And so from there, we can kind of solve for our pressure at A, right? We can just basically just subtract this term over, and then we'd have everything set equal to A. And that's our absolute pressure, right? There's a difference between absolute pressure and gauge pressure. So your gauge pressure would just be like whatever you get for PA minus 10 to the 5th pascals. Because your gauge pressure is equal to whatever pressure you're looking for minus 1 atmosphere, basically, which is 10 to the 5th pascals. But yeah. But yeah. .47 kilopascals. You're off by some amount. Four times 10 to the 9th. Whoa. Okay, there we go. 146,000 pascals. That's more what I'm looking for. Four times 10 to the 9th is like a zoinks moment right there. And then, but you were close with like the 47 kilopascals, because I mean, if you just add another 100,000 to that, then you're good. But you might have missed just that part. But yeah, 146,000 is what you should be looking at for the pressure at A, and that's the absolute pressure, like I said. 146,000 pascals. Oh, I just noticed someone did get 140. Leslie, so for 140, did you round by any chance somewhere, or did you miss a number? Did you not add a number somewhere, add a term? Yeah, it definitely should be 146. Okay. Yeah. Go ahead and check it. Just to be sure. But you got it. Okay, awesome. I was about to say, like, the 4 times 10 to the 9th really had me worried there. No worries. No worries. And honestly, like, sometimes it's hard to do a sanity check because low-key, I think on my last physics exam, I don't know, they literally had like, it was like half a particle, and they were asking for like the speed of it or something, and I swear to you, it was zooming. It was like, it was such a small particle, but like, I mean, I guess it makes sense that it would be really fast, but it just, with the values that they gave us, it really seemed like a ridiculous number. I got something like, I don't know, like 1.5 times 10 to the 8th meters per second. I can't remember what something about the problem made that feel like an unrealistic value. I can't remember, like, obviously if it's a particle, like, sure, like, that kind of might make sense, but there's something specific about the problem I can't remember. But yeah, sometimes it's just hard to do a sanity check because, like, you look at the problem and you're like, what the heck. And that's not even the worst problem, because I remember on an exam that we had last year where we were doing like viscosity and like Reynolds number and stuff. Yeah, they had a toaster floating in honey, but I guess no one noticed that the toaster was like owned by like a fairy or something, and the viscosity and like all the other values that they were calculating were like giga small. And so yeah, and we got like really small values, and you could like audibly and visibly see like the confusion in the room. Like, people were just like looking up at each other, like just confused, like, what the hell is this toaster? Because it was just like, I guess no one read that the problem was like, this is an like, literally the first sentence of the problem was like, this is an extremely small toaster, and then it just continued with the rest of it. But I guess no one, like, everyone just overlooked that because it was the last problem of the exam and we weren't in the mood. But I think that was probably the most ridiculous problem that we've seen so far in terms of like how out there it was with the like situation or story. Anyway. Okay. Now everyone looks to be on the same page, so we're good. So with that, I'll probably move on to part D. Forget about the small toaster. So, okay, part D says, what is the height of the water in the vertical tube? So now we're just looking for the height, right? Which would just be this height here that we're looking for, right? So now we can use similar equation, right? Just without all the velocities and stuff, right? So we're going to do PA plus PGHA is equal to PB plus PGHB, right? And once again, we can set this is equal to A, and this is point B, right? So we know that the pressure at A was 146,000, right? And then we know, someone said before, that pressure at B was an atmospheric pressure, right? So it was 10 to the 5th pascals. Now we can arbitrarily set again our value for height at A to be 0, right? So this is just the bottom. And then height B to just be HB, right? So it would be like 0.16 meters or whatever it is. I don't know. So PGHA will just be 0, right? Because our height at A is 0. We can arbitrarily set that, like I said. And then we can kind of, plug in our values here. So we have 1,000 for the density again, times 10 meters per second squared for our gravity, and then HB, right? And then we can just kind of subtract this over and solve for HB. So the reason we don't use like any of the equations with like the velocities and stuff is that this area here is pretty constant. We're not changing up the flow or anything like that, right? Because this is the same cross-sectional area, so your speed isn't changing or anything like that. So you can just use the regular equation, PA plus PGHA is equal to PB plus PGHB, in order to figure out the height at B here. So we can set the height at A as 0. We know the pressure at A, we know the pressure at B, and we can figure out the height at B. But yeah, and that should be around 4.6 meters, I believe. Make sense for part D? Any questions at all? Nope. Okay. Alrighty, so now we're at part E, basically, and F. We don't have much time left, so hopefully I can get through this in a reasonable amount of time. So part E is asking, so if we have the inflow pressure at the left entrance increases, then the height of the water in the tube would increase. Well, okay, sorry about that. My headphones just died, so hope you guys can hear me though, still, right? Can you guys hear me now? Hold up. Alright, 1 second here, because my mic is busted, so I don't know what's going on. Okay, can you guys hear me now? Okay, so sorry. I don't know what happened there. I think either my headphones died or they disconnected or whatever, but they just refused to connect back. Anyway, yeah, I was saying, okay, so height of the water in the tube would increase. If this height changed to 2h, what would the new outflow speed of the tube be? So, okay, inflow increases, height of the water in the tube would increase. If this height changed to h nu equals 2h, what would the new outflow speed be? Okay. Alrighty. So we're gonna have a change in speed. Our height is doubling effectively. So okay. Well, first of all, since our height is doubling here, right, from 4.6 meters to that would be 9.2 meters, right? Then our pressure at A would change, right? Because if you kind of think about this equation again right here, if we just, if we kind of solve for the new pressure at A, right? Because the pressure, as I said, the inflow pressure increases, right? So the height is increased. Well, I want to figure out now what the pressure is, the new pressure at point A would be. Because if this inflow pressure increased, right, then this pressure right here is going to change as well, right? So I want to figure out what the pressure is at A when I already know that the pressure at B is atmospheric pressure, and then I know that the height is doubled, right? So I can just do PA plus PGHA again is equal to PB plus PGHB, right? Like I said before, HA, that's 0, because I can set that arbitrarily to be 0 meters just at the bottom. And then I can solve for the pressure at A, given the pressure at B and the height at B, which is doubled. So if you got 1.3 for your height, let me check my answer, maybe I missed something. So I had 146,000 minus 10 to the 5th, and then divided by 1,000, and then divided by 10. Yeah, that should give you 4.6. Yeah, I might have made it like a small math error here or there. But, so yeah, now our height is doubled, right? So PA, and this is 0 again, right, is equal to 10 to the 5th plus 1,000 times 10 times 9.2 meters, right? Because our height doubled from 4.6 to 9.2 meters. So if we do that, we can get a new pressure at point A of 192,000 pascals, right? That's our new pressure at A. So with our new pressure at A, now they're asking us basically what would the new outflow speed of the tube be. So if we have an increased pressure at A, well, that'll change up what the speed outgoing here is, right? And so how can I figure that out? So first of all, I kind of want to think about what the speed at VB is going to be, right? So I can kind of think about the continuity equation again, right? So I know that AA times VA is equal to AB times VB, right? Because I know that the velocity is going to change, or the speed is going to change one way or another because I'm changing the pressure, right? And kind of going back to that whole artery question, right? So if I change the pressure, like if I want to increase the speed, right, I have to change the pressure somehow. So I want to see how that speed is going to change as a result. So I can look at VA, right, is equal to AB times VB over AA. And the reason why I kind of want to set this equal to VA, right, is that I want all my variables to be the same in the larger like equation where there's all the variables included. So like this equation, PA plus PGHA plus half PVA squared is equal to PB plus PGHB plus half PVB squared, right? So I don't want to have two variables, right? Because I don't know what this VA is going to be. That's unknown to me. But what I want to figure out is VB, right? So I want to substitute VA and change that to VB somehow. And so I can do that by kind of figuring out what VA would be in terms of VB, right? So I know that the cross-sectional area of point B, right? So this cross-sectional area here is 5 centimeters squared, right? And then I can multiply that by VB, and divide by the cross-sectional area of A, which was the 10 centimeters squared, right? So this should be like VB over 2 then. So this should be VB over 2 for VA, right? So that way I can basically take this value, this VA right here, substitute VB for it, right? So I can only solve for VB because I don't want two variables that I'm solving for at the same time, right? Otherwise, I mean, I don't know VA and I don't know VB. Then I'd try to solve for two variables and I can't do that, right? Because I'd have to have one or the other, basically, that I know. So now that I have this relationship here that I know that VA is equal to VB over 2, well, that means that the velocity, right, at point B is, or like half the velocity of point B is equal to point A, right? So I can kind of substitute that in to these values, and so I can just kind of write everything out. So I have 192,000 pascals for the pressure at A. This ended up being 0 because I set the height at A to be 0, remember from before, right? So then this is added to half P times VB over 2 squared, right? This is VA. And then PB is atmospheric, so 10 to the 5th pascals plus 1,000 times 10 times the height at B, which is 4 meters, right? Let me move this over. And then this is plus 1/2 times 1,000 times VB squared. Oops. So this is pretty much the entire equation set up right here, right? And then from that we can kind of do our own manipulation and solve for VB. So to kind of reiterate, right, we have an increase in the inflow pressure, right? So that'll change the pressure at point A, and we can figure that out by this piece of information. We know that the new height of the vertical tube is 2h, right? So 2 times 4.6 is just 9.2. And then using this equation right here, we can figure out the new pressure at point A just by doing the pressure at B plus PGHB, right? So we know that pressure at B, since it's in contact with the air, it'll just be equal to the atmospheric pressure. So we'll just add that to 1,000 kilograms per meter cubed times 10 meters per second squared times our new height, which is double the old height. So 2 times 4.6 is 9.2. That'll give us a new pressure at point A of 192,000 pascals. And then we know that since there is a change in pressure, there's going to be a change in the speed, right? So the flow has to stay the same, but since you made a change to the pressure, you're going to make a change to the velocity one way or another, right? So then we want to figure out what this new velocity is, what this new VB is, right, at the end, at the outflow here, what this new velocity is going to be. So I can kind of set up this big equation here that I know includes the velocity and the pressures and the densities and all that, right? But I don't know what VA is, so, and I want to just solve for VB, right? So if I'm just looking to solve for VB, I want to like basically rewrite this equation in terms of VB. So I can change this VA and solve for VB by looking at the continuity equation and realizing that, well, if I kind of solve for VA, right, I can get it in terms of VB. So I know that area at A times the velocity at A is equal to area at B times the velocity at B. Solving for VA will give me AB VB over AA. And then I can substitute the value that I know, the cross-sectional area of point B, which is the 5 centimeters squared. And then divide by the area of A, which was the 10 centimeters squared, and that'll give me VA is equal to VB over 2. So then, since I have this in terms of VB, I can basically just throw it into this equation, right? So now that I have VB as the only variable that's unknown, right? And then I can solve for VB, And I hope by the time I kind of like reiterated all this stuff, you should have gotten like VB close to like 12 meters per second. I think I got like 11.8 or 11.78 meters per second for VB. But yeah, does that make sense for part E? Okay, cool. Any questions at all? Because I know that was kind of a multi-step process, and it was might have been hard to follow. But yeah, if there aren't any other questions about part E, we can move on to part F, and wrap it up for the night. And then just as a side note as well, like as always, like just feel free to send me an email or anything if you guys have any other questions about the written homework at all, if anything's not making sense, or if you need additional clarification, as well as the online homework. I know I don't have like a dedicated day for the online homework because I figured like other peer leaders cover that as well. And I just feel like the written homework's like usually more beneficial for prep for like quizzes and stuff, just because it kind of helps you to build like those problem solving skills, and the problems are usually closest to the quizzes and the exams and stuff. But I'm always more than willing to answer any questions about the online homework. I might not be as active with the GroupMe just because I have a ton of GroupMe, so like sometimes I'll just shut off notifications or whatever. But I'm always there for like my emails, so if you have any questions, just feel free to send me an email, and I'll try to get back as soon as possible with explanations about any of the written homework problems as best as I can. And for those who I've helped out in the past with online homework problems, you guys can vouch for me, I suppose. Like I might not always be like 100% on time with like getting back to you, but I try my best given I don't have anything else major going on. But yeah, so yeah, feel free to ask any questions anytime, and I'll try to get back as soon as possible. But that kind of brings me to part F. So it says if all of the water is replaced with oil with a density of 0.75 times the density of water, then the vertical tube is filled up to the same height. So now it's asking what is the new pressure at point A. Well, this is kind of redoing what we did for the first part of E, but now we're kind of figuring out pressure instead. So we know now that the height will be the same, so 4.6 meters for that vertical tube. But now we're replacing the water with oil, right? And now I want to figure out what the pressure is at point A still. So pressure at point A is unknown, right? Then I have PGHA, right? PB plus PGHB, right? So I want to figure out A. I know, like I said before, 1,000 times, the height was 0. That's my arbitrarily set point. So this whole value would be 0. And then PB is in contact with the atmosphere, so that should be 10 to the 5th pascals, right? And then looking at the density here, well, the density here, P oil, should just be equal to 0.75 times the density of water, which is 1,000. So that means that the density of oil will be like 750 kilograms per meter cubed, right? So given that information, I can just figure out the pressure at point A by plugging some values in. So I have PA is equal to PB, which is the 10 to the 5th pascals, which is the atmospheric pressure, plus the 750 kilograms per meter cubed, which is the density of the oil, times 10 meters per second squared, times the height, which is 4.6 meters. And that'll give me the pressure at A with this oil, right? So yeah, that should give us the pressure at point A, given this new density with the same height, that is. 134,500. I got closer to 135,800, but let me check my answer real quick. But I mean, shouldn't be a big deal. I don't think so. 750 times 10 times 4.6. Yeah, I don't know how I got. Maybe I had rounded something in the past or whatever. I don't know. But yeah, 134,500 pascals is right. But yeah, that takes care for part F and all of problem 3 there. So hopefully that helped. Sorry we went over time, and yeah, I hope you guys enjoy the rest of your night, and I will see you on Tuesday, I believe, for the quiz session. And I saw that some people entered late, so I apologize if they haven't like fixed my schedule to align with like the 4 to 6 p.m. sessions now. So I will contact the MSLC again and the professor just to make sure that that was taken care of. So, but yeah, hope you guys have a awesome rest of your night, and I'll see you Tuesday.